Hi everyone, this is Sharan from BVC Engineering College, Vadalarevu. So today we can discuss about the concept of fabrication of a CMOS transistor. And coming to what are the topics we have to discuss today? And there is a overview of CMOS transistor, a CMOS fabrication process overview, a CMOS fabrication process, and problems with current CMOS fabrication, and future changes in CMOS fabrication. And coming to what is a CMOS? A CMOS technology uses both NMOS and PMOS transistors, and the transistors are arranged in the structure formed by two complementary networks, such as pull up network is complement of pull down. That means both pull up transistors as well as pull down transistors are both complement form. And coming to all are arranged in the form of a parallel to series or series to parallels. If pull up transistors are connected in parallel, the pull down transistors are connected in series. In the same way, the pull up transistors are connected in series. Similarly, the pull down transistors are connected in parallel. And simply you can observe the circuit here, a simple CMOS in circuit here, and this is about NMOS transistor, and this is about PMOS transistor. And coming to the CMOS fabrication, and it includes CMOS transistors are fabricated on a silicon vapor with a required thickness based on the technology size. The transistor size should be depends. So generally we have different types of technologies. In the olden days we have 250 nanometer technologies, after then 180 nanometers, 150 and 130, and after then 90, 45. Nowadays we are using 7.5 nanometer technologies. So based on the type of the technology we are using, the size of the transistor will be depends. And coming to the different types of vapor diameters, and lithography process similar to like our printing press, and on each step different materials we are depositing, and easiest to understand by viewing both top and cross sectional view of a vapor. And coming to a simple example, inverter cross sectional view, and in this case typically use a p-type substrate for NMOS transistor, requires to make N-well body of PMOS transistor. So generally the CMOS transistors are implemented in different ways based on the technology. Generally we have N-well process and P-well process and twin tap. So coming to in our today's session, we are discussing about the concept of N-well process. So coming to this is about inverter masking set. Simply this is about top view, and transistors and wires and different defined by mask, and cross sectional taken along dasher line. See this is the dasher line here, and it's about dotted lines masking, and detailed mask use. What are the different types of masks we are using in the fabrication process? We can list out all these. So total we are having 6 masks. Those are N-well, polysilicon, N-diffusion, P-diffusion, contact, and metal. Okay, these are about all these. And coming to the process of fabrication, now we can enter into the fabrication process. So coming to the first step is selection of the substrate. And coming to based on the type of the process we are using for the fabrication, the substrate will be depends. If you are using N-well process, definitely has to be consider the P substrate. Otherwise, if you are using P-well process, definitely has to be used N substrate. That is the base material for the designing of a transistor. So coming to this, start with a blank vapor. Simply that is a silicon vapor with a thickness of 1 micrometer like that. And coming to this, after that build inverter from the bottom up. So first step will be from the N-well process. In this case we are using N-well process, and cover vapor with protective layer, that is the material of silicon dioxide SiO2. And after then we has to use different processes. Those are remove oxide layer, where N-well should be built. And after then implant or diffuse N dopants into the exposed vapor to form N-well. After then strip off SiO2. Here the strip off means simply we has to be remove the excess SiO2 material from the substrate. And coming to the next one, oxidation. Okay, that is the second process of the fabrication, that is oxidation. Here in this process of oxidation we are using silicon dioxide with a thickness of 1 micrometer and to the entire surface of the P substrate. Okay, and the material is silicon dioxide SiO2. And after then, and the main purpose of this oxidation is to protect the entire surface of the silicon vapor. And coming to the third step, so depositing of photoresistive layer, that is simply a spin-on photoresist. So photoresist is a light sensitive organic polymer. So property changes where exposed to light. When any light is superimposed on the photoresistive layer, the property of the photoresistive layer will be changes. That's why you're using the photoresistive layer here. And coming to the two types of photoresistors you have, that is positive or negative. So positive resist can be removed if exposed to UV light, and negative resist cannot be removed if exposed to UV light. Simply here, so positive resist means if we are using UV light should be superimposed on the vapor, simply it will be removes the photoresistive layer on the vapor. If you are using negative resist means if you are exposing of UV light, it never be removes the photoresistive layer. That is about the third step about photoresistive layer. And coming to the fourth one, simply we are passing some UV light. See here, expose photoresistive to ultraviolet light through the N-well mask. Here the N-well mask means here we are using N-well where we want to be place the well, that is N-well. In that case we are using some mask here. See this is the mask, and I want to be place the N-well here. That's why we can use the mask here. And coming to the strip of exposure photoresist with chemicals. So here any excessive photoresistive layer will be there, that should be removed with the help of some excess chemicals. There is nothing but hydrofluoric acid, that should be discussed in the next slide. And see here, there is nothing but etching. Etching means etch oxide with hydrofluoric acid. So only attacks oxide where resist has been exposed. So N-well pattern is transferred from the mask to silicon dioxide surface, creates an opening to the silicon surface, and this is about this. And coming to the strip, so photoresist. Simply we are previously discussed, if there any excessive photoresistive layer will be there, that should be removed. That is nothing but strip of remaining photoresist and necessary, so resist does not melt in the next step. And coming to the swell, here we are using the N-well process. That's why it has to be create one N-well here. The N-well is formed with diffusion or ion implantation, and after then we has to be go with the diffusion. So place vapor in furnace with arsenic rich gas and heat until arsenic atoms diffuse into exposed silicon. After then ion implantation, so blast vapor with beam of arsenic ions, and ions blocked by silicon dioxide, there is SiO2, only enter exposed silicon. And after then, so silicon dioxide seals areas which remains p-type. So after then, so strip oxide. So strip oxide means on the entire surface of the substrate some oxidation layer will be there, that I want to be remove that by using this strip oxide. In this case, observe here, there is no oxidation layer here, that should be removed by using hydrofluoric acid. That is about, so strip off the remaining oxide using hydrofluoric acid. And after then, so polysilicon, so self-aligned gate technology. Here the depositing very thin layer of gate oxide, again has to be diffuse some silicon dioxide layer will be has to be some very thin layer, and after then so chemical vapor deposition of silicon layer, that is about CVD. So place vapor in the furnace with silane gas, that is SiH4, and forms many small crystals called polysilicon, heavily doped to be good conductor. And after then Simply here has to be placed polysilicon where I want to be design the gate terminal. Here the main intention to place the polysilicon here, at which place we want to be make the gate terminal. Here in the CMOS transistors we have NMOS transistor as well as a PMOS. For both NMOS transistor as well as PMOS transistor we have one gate terminal. Okay, for each transistor has to be used one gate, that's why has to be placed polysilicon here for the one transistor, and this is for one more transistor. And here in the annual process we can able to place a PMOS transistor, and remaining second case we are using here NMOS transistor. And after then, so self-aligned process, use gate oxide. Again has to be use some silicon dioxide material, again has to be superimposed on the entire vapor. And after then the diffusion process. Okay, so for the NMOS transistor or PMOS transistor, excluding gates, we are having two more terminals, those are source and drain. Okay, those two terminals should be designed with the help of diffusion. Okay, for the NMOS transistor it has to use N diffusion, and for the PMOS transistor we has to use P diffusion. So coming to here the diffusion concepts, so pattern oxide and form N regions. So self-aligned process where gate blocks and dopants. So polysilicon is better than metal for self-aligned gates because it does not melt during later processing. And see here, and this is for NMOS transistor and this is for PMOS transistor. And see here, this is about the diffusion, and see this is N plus diffusion, and here N plus diffusion for the NMOS transistor, and this is the gate terminal, and this is source, and this is drain. These are the three terminals for the NMOS transistor. Okay, here historically dopants were diffused, usually high energy ion implantation used today, but N regions are still called diffusion. And coming to the N diffusion, strip off oxide to complete patterning step. Here again has to be remove the entire oxidation layer. And coming to the P diffusion, previously we can discuss N diffusion, now coming to the P diffusion. Similar to the set of steps for the P diffusion as same as N diffusion. Here see this, these are the P diffusions you has to use by using P diffusion masking as same as N diffusion masking. And here this is the gate terminal for the PMOS transistor, and this is for the source, and this is for the drain. And after completion of these transistors, now the transistor formation is over for the CMOS, and this is PMOS transistor, and this is NMOS transistor. Now I has to use some contacts. Now we need to wire together the devices. So cover chip with thick field oxide, H oxide where the contact cuts are needed. Simply generally for the transistor where we need the contacts, okay, those should be etched. And after then metallization, okay, so spotter or aluminum over whole vapor. Simply here the metal deposition has to be needed for the entire vapor. For that metal it has to use aluminum. So copper is used in new technology, so nowadays we are using copper. In previously we are using, most of the cases we are using aluminum. And after then pattern to remove excess metal leaving wires. Is there any excess metals or wires will be there, those should be removed. And coming to this, what are the problems in current CMOS fabrication? Those about, optical lithography is limited by the light frequency, and material limitations, and yield limitations, and space limitations. These are the problems with current CMOS fabrication. And coming to the future changes in CMOS fabrication, what are the future changes? And coming to the first one is material changes like using high K materials, and design changes, that is silicon on insulator, and double gate, that is FinFET, and twin tub process. Thank you.